The universe is filled with wonders, celestial tapestries of light and color. Yet for millions on Earth, this cosmic beauty remains unseen. Vision loss, a global health crisis, affects a staggering number of people. Imagine a world shrouded in darkness where the simplest tasks become daunting challenges. This is the reality for over 2.2 billion individuals worldwide living with blindness or severe vision impairment. The World Health Organization paints a stark picture. 253 million people are visually impaired. Of these, 39 million are completely blind. The economic burden is significant. Lost productivity, healthcare costs, and the need for assistive technologies place a strain on resources. Vision loss can lead to isolation, depression, and a diminished quality of life. Imagine the simple joys we often take for granted: reading a book, watching a sunset, seeing the faces of loved ones. In the quest to restore sight, a new hope emerges. Bionic eyes, a testament to our ingenuity and our unwavering pursuit of a brighter future. For centuries, the idea of restoring sight to the blind seemed like something out of science fiction, but what was once a distant dream is now within reach. Bionic eyes, marvels of modern medicine and engineering, offer a beacon of hope to those living in darkness. These devices work by bypassing damaged parts of the visual system and directly stimulating the remaining healthy cells. Bionic eyes consist of several key components: a tiny camera, a processing unit, and an implant that interfaces with the eye or brain. The camera captures images, which are processed by a microchip and converted into electrical signals. These signals are wirelessly transmitted to the implant, stimulating the remaining healthy cells in the retina or visual cortex. Imagine a tiny, intricate device smaller than a grain of rice, implanted within the delicate layers of the human eye. This is the reality of retinal implants, a groundbreaking approach to restoring sight. The retina, a thin layer of tissue lining the back of the eye, is essential for vision. It contains specialized cells called photoreceptors, rods, and cones, which convert light into electrical signals. In many eye diseases such as retinitis pigmentosa and age-related macular degeneration, the photoreceptors are damaged or lost, leading to vision loss. Retinal implants aim to replace the function of these damaged cells. The implant receives wireless signals from a small camera mounted on glasses, converting them into electrical pulses that stimulate the remaining healthy retinal cells. The stimulated cells then send signals to the brain via the optic nerve, creating a visual perception. While retinal implants cannot fully restore normal vision, they can provide a remarkable level of sight for those who were once blind. This newfound vision can make a world of difference, enabling greater independence and improving quality of life. Cortical implants take a bolder approach, bypassing the damaged visual pathway altogether and directly stimulating the brain's visual cortex. This region, located at the back of the head, is responsible for processing visual information from the eyes. Cortical implants consist of a grid of electrodes surgically placed on the surface of the visual cortex. These electrodes receive wireless signals from a small camera, similar to retinal implants. The signals are then converted into electrical pulses that stimulate specific neurons in the visual cortex, creating the perception of light. Imagine a piano keyboard representing the visual cortex, with each key corresponding to a different point in our field of vision. When an electrode in a cortical implant is stimulated, it creates a point of light in the patient's visual field. By stimulating multiple electrodes in a specific pattern, researchers can create more complex visual perceptions, such as shapes, letters, or even simple images. While still in its early stages, cortical implant technology holds immense promise for those with profound vision loss. The human brain is a marvel of evolution, processing vast amounts of information efficiently. Restoring vision with bionic eyes is challenging, requiring sense-making of the visual world. AI helps decode complex patterns of light and shadow for bionic eyes. Traditional bionic eyes use simple algorithms to process visual data. AI is revolutionizing this process. Machine learning algorithms analyze visual information in real time, identifying objects and faces. AI-powered bionic eyes provide real-time information about the environment. This offers independence and awareness for individuals with vision loss. AI personalizes the visual experience, optimizing perception. The field of bionic eye technology is rapidly evolving, with new advancements emerging all the time. From higher resolution implants to more sophisticated image processing algorithms, researchers are pushing the boundaries of what is possible. One exciting area of research is the development of wireless bionic eyes. Current implants require a wired connection between the camera and the processing unit, which can be cumbersome and limit mobility. Wireless systems would eliminate the need for these wires, providing greater freedom and discretion for users. Another promising avenue is the use of stem cells to regenerate damaged retinal tissue. Stem cells have the remarkable ability to develop into different types of cells, including photoreceptors. Researchers are exploring ways to transplant stem cells into the retina, where they could potentially replace damaged cells and restore vision. Beyond the laboratory, the true measure of success lies in the lives of those who have been touched by this groundbreaking technology. Around the world, individuals who were once blind are now able to see their loved ones' faces, navigate their surroundings, and even regain some degree of independence thanks to bionic eyes. As we gaze toward the horizon of scientific discovery, the future of bionic vision shimmers with extraordinary possibilities. Imagine a world where bionic eyes restore vision and enhance perception. Future technology could allow us to see in the dark, perceive ultraviolet light, and zoom in on distant objects. Integration with augmented and virtual reality could open new realms of experience. Imagine the visually impaired navigating complex environments and accessing real-time information. Continued research and clinical trials are crucial to unlocking bionic eye technology's potential. Collaboration between scientists, engineers, and policymakers can accelerate innovation. Let us embrace the challenge of vision restoration with determination and hope. Together, we can illuminate the darkness and create a future where sight is available to all.